In this example, we have a parallel plate capacitor with a capacitance of 1 microfarad. And this thing is connected to a battery that's going to maintain the potential difference at 5 volts throughout the entire example. And after doing some preliminary calculations in part A and B, we're going to insert a dielectric of constant 2.0 and try to calculate some of the changes that occur with the capacitor. So first off, I want to compute the original charge on the capacitor, and this goes back to the definition of capacitance. I'm going to go ahead and call it C0 because the capacitance is going to change starting in part C. So capacitance is charge per volt, and if I want to find the charge on a capacitor, I just take the capacitance and multiply by the potential difference. And in this case, that's 1 microfarad multiplied by 5.0 volts, and I'll get 5 microcoulombs of charge. In part B, we're asked for the original energy in the capacitor, and 1/2 CV squared will get the job done. I have the capacitance as 1 microfarad, and then I have my potential difference as 5 volts. I'm going to square that. I'll just go ahead and write this in scientific notation, and I get 1.25 times 10 to the negative 5 joules. Now I want to compute the new capacitance when I add the dielectric into the capacitor, and I'll call that C. And that's just given by kappa times the original capacitance. I just multiply by the dielectric constant, so I get 2 times the original, which was 1 microfarad. So now it's 2 microfarads. In part D, I'm asked to compute the new charge on this capacitor when the dielectric is added. So this is where you have to start thinking carefully about what's going on here. When I add that dielectric into the capacitor, for a brief moment, the electric field is diminished between the plates, and that means the potential difference is diminished between the plates. And that battery, because it's still connected, is going to react by pumping more charge onto the plates to get that potential difference back up to 5 volts. So the charge should increase here. As far as getting the math done, it's as simple as writing down again the definition of capacitance and solving for Q. And I know the potential difference is going to stay at 5 volts because this thing is connected to the battery. And my capacitance is 2 microfarads. And my potential difference is 5 volts. And I end up with 10 microcoulombs of charge. Finally, I want to compute the new potential energy in this capacitor. And I'll do that with 1/2 CV squared. Up in part B, I'm going to change that C to a C0 because that was before we added the dielectric. And just to stay symbolic for a moment, I know the capacitance changes to kappa times the original capacitance. And I know that V is staying the same because I'm connected to a battery. So I could just pull the kappa out in front. And the point of that is to highlight that my potential energy has actually gone up by a factor of 2 here. So I'll call it 2 times PE original. So I get 2.5 times 10 to the negative 5th joules. This is in contrast to what happened to a capacitor that was disconnected from the power source. In that case, the potential energy actually went down. And I'll post a link to the video where we did that example. So finally, we're asked for the change in potential energy, and I just found out that it went up. It went from 1.25 to 2.5. So that's an increase of 1.25 times 10 to the negative 5th joules. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.